how to find the derivative of an exponential function. Here is a graph of the exponential function y equals 2 to the x. So make a quick sketch at home and then just try to sketch what you think the derivative of this function would look like. Okay, are we done? So I hope you realized that the slope here is close to 0. I know this graph makes it look like the slope is 0, but as we know, exponential growth, the slope is never going to be 0. The slope is positive but close to 0, and then the slope is getting more and more and more positive. So the derivative is going to look like this. Drum roll, please. Boom. Oh, interesting. So I'm sure when you made your sketch, you didn't know exactly where the derivative would be. It looks as though the derivative is a little below, if you will, the original function. Huh. What type of function do you think the derivative is? Yeah, it certainly looks exponential. Interesting. Interesting. What if I told you that I know the actual equation of this derivative? The actual derivative is, and I'm using my calculator, which is a hint, the actual derivative of this is about, because I'm about to write a four decimals of an irrational number. Ooh. Where did I get that number? Interesting. All right, let's try this now with 3 to the x. Y equals 3 to the x. Boom. Oh, okay. So it's going up a little more quickly. So in other words, instead of this derivative, instead of this function doubling for every x, it's tripling for every x, right? Times 3 times 3 times 3, getting steeper and steeper and steeper. But yes, you're right. The derivative would also be an exponential. Let's see what the derivative looks like. Drum roll, please. Wait a minute. In this instance, the derivative looks like it's a little above, if you will, the original function. What if I told you that the derivative of 3 to the x is about equal to 1.0986 times 3 to the x? What the? Where am I getting those goofy numbers? So it seems as though the derivative of an exponential function is an exponential function. Y equals 2 to the x, the derivative was a little under it. The derivative of y equals 3 to the x was a little above it. Think about what type of exponential function might have its derivative be right on it. Any ideas? What is a cool number that's between 2 and 3 and shows up all the time in exponential growth and exponential decay? Y equals e to the x. Y equals e to the x. This is just kind of mind-boggling to me. Y equals e to the x is an amazing, amazing example of exponential growth because its derivative is, drum roll please. Wait a minute. Derivative again, drum roll please again. Oh my gosh. The derivative of e to the x is e to the x. That is mind-blowing. Think about what that means. What that means is that the y value of this function is equal to the slope. So when the y is 1, the slope of the function is 1. When y is 2, the slope of the function is 2. When y is 6, the slope of that function is 6. That's just mind-blowing. but it's true. Okay, so let's use those 3 examples to see if you can come up with how I found the derivative of each of these. The derivative of y equals 2 to the x was this. The derivative of y equals 3 to the x was that. And the derivative of y equals e to the x was that. There's a cool shortcut trick. Pause the video, play around with your calculator. If you want another example, I'll give you another example. Give me a number. 5, sure. Okay, let's say I wanted to find the derivative of y equals 5 to the x. Y equals 5 to the x. Its derivative would be approximately 1.6094 times 5 to the x. Play around with your calculator. See if you see what cool thing I'm doing. Did you figure it out? Don't zip ahead. Figure it out. Grab your calculator. Play around. It's so much more fun to do it. All right, what's the shortcut? The shortcut is if you have y equals some number to the x, the derivative is going to be the natural log of the base times b to the x. Well done. So, 0.6931, that's a decimal approximation for the natural log of 2. So the derivative of 2 to the x is the natural log of 2 times 2 to the x. This right here, 1.0986, that's a decimal approximation for the natural log of 3. And wait a minute, what's the coefficient here? Ah, it's 1, because the natural log of e, if we recall, is 1. How cool is that? Now, before we finish, I just want to quickly plant the seed. We'll talk about this a little later. Is the chain rule applies, as it always does. So, for example, if I had y equals 3 to the 5x squared plus 1, I'm going to use my new little cool shortcut. And I know the derivative of an exponential function is the natural log of the base times the exponential function as it is. But the chain rule says whenever I have a function inside of a function, then the chain rule is the derivative of the outside function times the derivative of the inside function. And what is the inside or the input of an exponential function? It's the exponent. So, in this case, the derivative of an exponential function would be the natural log of the base times the exponential function as it is, times the derivative of the inside. So this would be the derivative here. So, in a more general way, my shortcut for finding derivatives of exponentials is if I have a function where b is some constant and it's raised to u, where u is some function in terms of x, my derivative would be the natural log of the base times b to the u times the derivative of that exponent. And that's the chain rule component. Okay? So here's the shortcut for finding derivatives of exponentials.